So I would need somebody to help me test the the YouTube live, see if it's working. So I believe now it's open.
This is true. It is working.
Can somebody please help?
Letian, can you check?
To test the YouTube live.
It's working. Yeah, it's working.
Awesome. Thank you. Okay. So next, I'm going to share my window. So let me know if you can see my desktop screen. Yep. Okay. So excellent. So I believe we are most people are here already. So shall we start now?
Yeah, I think so.
Okay.
Yeah, I think some other people, I think they are not available on Saturday. So
sure, that's okay. So please, you guys, let me know if you need additional help. I cannot see the full screen. So today, I hope last time I talked about AI, big data, and machine learning. So in this case, today we are going to give a real class, like hands-on, to see how we can use machine learning to solve real-world problems. But before we jump into the problem, I want you guys to think, right? So first, let's say I give you two pictures. One is cat, one is dog. How can you know whether this is cat or dog as human? So anybody want to give it a try? The picture itself, think about, it could be, anything, right? You just random take a photo, and within the photo, maybe there's a cat or maybe there's a dog. How would you recognize it? Anybody want to give it a try?
Well, you can start off by looking at like how big the thing is. Like chances are larger, or in some circumstances, larger objects are dogs and smaller objects are cats.
Not always. There are small dogs as well.
Yeah, well, there's small dogs, yes. But first and foremost, think about the picture itself, right? So within the picture, there are actually, so many things, right? It could be, there could be dogs, there could be trees, there could be houses, right? First, how do you know? There's, how do you know where you should look at it, right? That would be the first question that we need to solve as human. We first, look at the whole big picture. We found out, oh, there's an animal somewhere, and we want to figure out whether that's cat or dog, right? So we first figure out, zoom into that area and find out a thing. And then the next one, after we know this thing, right, this animal, right, we start to well, Latian says use Google image search. That's good one. You could do that, but Google image search is also use machine learning. That's something we want to solve here. Right?
Letian, that's cheating. You just think about it. When you look at a picture, you just think, oh, this is a cat, this is a dog. You will not think about anything else. Like there is no other things that you want here. Right. You will just get it.
So let's then look at the second one. So now I'll give you an image, remove all of the surrounding things. I just give you the, one is cat, one is dog, right? Just themselves. Imagine everything else is being removed. So now how do you tell which one is cat and which one is dog? You probably look at, hey, how about their face, their fur, their eyes, right? Their total shape, right? So those are the, characteristics that you want to look at, right? And then at last, even if you try so hard, there are some cases, that look like a cat and a dog, right? There are some such animals, right? Like, the cat is really similar with the dog, right? So that happened, right? So those are tricky parts, right? And we as humans, somehow at the end of the day, we have to arbitrate, all these decisions and say, oh, this is cat, this is dog, right? Like just looking at it, right? But obviously we have gene techniques, to further identify this is cat or dog, right? Those are a little bit different, different kind of technologies, right? So here today we are going to learn by just looking at the picture itself, how we can tell, whether this is cat or it's dog. And not only we as humans can actually reason about it, we are going to learn how we can teach a computer to do that, right? So then in the future, maybe Latin, like what you said, right? When people, when you upload a photo, ask Google, or maybe ask, a website that may be, right? And we're going to tell them, oh, based on my analysis, this is cat or this is dog, right? That's the goal today. And the steps that we're going through is pretty much what we have just discussed previously, to find out, zoom into how this is the animal area. And then based on the animal, we find out the characteristics, and then we somehow, draw a conclusion, this is cat or it's dog, right? Let's see how we can use AI, use machine learning to learn that, right? So I will, first, anybody know this, PyPB? Have you guys opened on your window? You can open it in a separate window. Just open the link that I shared in the chat. Anybody hasn't opened it yet? Okay, thank you, Letian, for posting the link again. Yeah, so let's. I assume you already open, right? So very quick, if you look at this PyPB file, right? So this actually is a Python code that runs on the cloud, in the cloud. That if you look at this one, just quickly scan through them. There are two different types of things. One is it's a text, right? Text, you can read the information, right? And one is code. Code you can write. How do you write? Right? There are several ways. If you click the code, and there's on the left side there's a run cell. You can click that run cell to run it. Or usually I just use Shift Enter to run it. Okay. There are some other tricks. Eric, do you know any other tricks on how to run a cell? Eric, you're muted. Okay.
I do not.
Okay, that's excellent. Okay, that's fine. So, right. So learn about this, and for now, let's look at look at the first section. So as I said, we are building a convolutional network, that can recognize the dog and the cat, right? And we are going to first, go through these steps, right? First we look at the source data, the training data, and then we are going to build the network, and then we are going to train it, and then at last we are going to validate its accuracy, right? So this is a very typical small-scale machine learning algorithm, right? And let's keep going, explore the data, right? And this is the data that you can download from the website. For now, just click this wget that cell. On the left side, click run cell. Okay, it will take a while to download. Considering we have so many people, it could be slow, yeah. So just let it run. It will download and then save it there, right? So there are 2,000 JPEG pictures. Some of them are cats, some of them are dogs, right? And they actually are located. If you look at my left side, there's a files. If you click files, right, click the up, right? So then you will see this root directory, which is there's temp, right? As you can see, I already downloaded this file, cats and dogs filtered zip, right? So on the cloud, there's actually a virtual machine that you can use. You can put, when you download information, it's actually received locally on the local disk. Okay. So I talked about the cloud last time, but this time you guys are really using a machine in the cloud. Okay. So then let's run the second one. try to unzip it, right? The zip, I assume you guys know what it does, but if you don't, right, the meaning of it is basically previously when you download it, all of the image files are saved into one single file, zipped together, compressed, and then by using this, zip file.zip file, this function, that we can unzip this file into the folder. As you can see on the left side, now I'm having this folder now, cats and dogs field. If you click it, you can see the structure. There's a train directory, which is used to train the data. There's validation directory, which is used to validate our trained, machine learning algorithm, how effective they are, right? And if you look at the train side, right, there are cats and dogs directory. This is how the covers this machine learning algorithms. How do they label them, right? For the cats, the directory name shows the label for all the images in that category, in that directory, and dogs, we use that directory name as the label for every image in that directory. I'm going to look at show some dogs here. As you can see here, the dog name, it doesn't matter. Dog0.jpg, you can call it dog something.jpg or dog abcd. Either way is fine. The name of the JPG file doesn't matter. Okay, so now double click it. You can see the kill dog. Okay, this is the raw image that we're talking about. Maybe I can try one cat as well. See? Right, this is cat. So
yeah.
So let's keep going. So after you zip it, after you unzip it, you already get this directory. Remember that for now, okay? And then run the bstrr, this one. So what does this do, right? This one is to so this one is just to show the directories. As you can see, if you want, you can look at for example this one, and look at here. Copy path, let's say. Okay. See, this is the path for all the training data there, right? So what we want in this code is to, for example, in the training dogs directory, it should be trained dog. Okay, so this is what we are trying to get here. Okay, so now let's run this code. And can I see the variable? Yeah, look at here, right? So on the right side, you can see this is exactly the directory that we're trying to get. So there's no fancy stuff here so far. Okay, let's keep going. So now this is the interesting part. We just as if previously I showed you the directory. Here we just turned them out, right? These are all the names of the images that we are getting, right? The cat and the dog, the top 10 file names, right? As I mentioned, the name of the file, it doesn't matter, okay? Only the label that matters, the labels is basically the directory name. And then the next one, we're going to get the statistics roughly. So as you can see, the training data, we have 1,000 images for dog and 1,000 images for cat. And the validation, we have 500 images each, right? This is just as if if you click the left side, you can find it out. It's just we use Python to get the same information. I want to point out that here it's important to think about the number of images that we're using. Here we use 1,000. Can I ask you guys a question? What do you guys think what is the minimum amount of images to train such a meaningful, machine learning model? Do you guys have any sense, roughly? Any guess here?
I'm not quite sure. Maybe like 200, 500.
200, 500. Okay, that's pretty good guess. Okay, but how about, let's say we only have 10 images? Can we train such a model? It's probably difficult, right? Even if let's say you teach a new kid who doesn't know dogs and cats, right? If you just let them see 10 pages and it's 10 images, and you tell them these are dogs, these are cats, right? And then you put out a new image and tell them, they would be faster. If they already see that, yes, it's easy. But if they haven't seen it, right, a new image, right, they would have trouble to know whether this is cat or dog, right? I believe when we are really young, sometimes we're confused as well, right? I cannot imagine, for example, even nowadays, right? It would be very, very difficult for me to recognize whether this is a dog or this is a coyote, or maybe this is a wolf, right? Those kind of things, sometimes it's a little bit fuzzy to me, right? So I would use additional context. For example, if I look at, I'm going to Yellowstone, I look at an animal that looks like dog, right? Most likely it's not dog, right? Because it's wild, it cannot be a dog, right? So I use those instruments to infer, right? But when we do machine learning training, so this machine learning training is just like a new baby that knows nothing in the beginning. So we have to feed them with enough data and train them so that they understand, oh, these are cats, these are dogs, right? And for that, it really depends on the machine learning, the neural networks, the complexity. If the machine learning, the neural networks complexity is really high, then you would need much more data. And if just for a very simple one, you probably don't need that much. For example, in today's model, later we're going to discuss about the model. My sense is, Kevin, probably you're right. If we only have 200, 300 images, we probably can train the model well enough that it can recognize both of the cats and dogs, right? But the accuracy maybe not that high, and we are going to talk about how we can evaluate the accuracy of these neural networks, right? So later let's go step by step. But for now, I want you to get the information that the amount of training data matters, right? If the model is more complex, you would need more training data, right? Okay, so let's keep going and run this one. So this one, this is just we just want to display the image. I think previously I already clicked it, you guys already see the image, but this one is just using Python to show all the the list of images all together. I have to click them one by one, right? Look, you can look at it, right? It's cute, all these cats and dogs, right? Now this actually, if you look at for example this one, it's a little bit hard to say whether it's dog or cat. It's, I mean, if I take a first look, it looks like a cat somehow to me, right? Okay, so anyway, let's do that, and then let's keep going, right? So in this section, I talk about the complexity of the neural network. What do I really mean? The complexity, right? So let's first look at the image itself, right? So before we do that, there's there are I believe there are some small things that we have to do. We have to normalize the data. Because the original image, if you look at that dimension, it's not exactly uniform. But when you train the data, it's critical to make sure the source data to be uniform for the machine learning neural network. This may not be true for all the machine learning networks, but typical machine learning network, right? We have to basically first resize the images to be uniform format before we can actually can train them. So let me see. This code doesn't have it. Okay. So for now, let's let me see where it does that. There should be one place that actually try to resize the image. Okay, when we reach there, I'm going to explain, right? But for now, let's look at this TensorFlow, right? So this is TensorFlow. We just import this library, and then really let's take a deep look at this TensorFlow itself, right? The TensorFlow says, oh, the input is 150 by 150 by 3. Why 3? Because each image pixel is RGB, right? It has 3 integers, right? And we have to somehow later we are going to transform each image into a 150 by 150 image, okay, uniform. And then we have the second layer that is going to ReLU. This is convolutional network, right? And I'm going to explain later, what exactly it does, right? And then we build this one, and then we use max pooling 2D, and then we build another layer. We have this one, and then at last we have, another layer. So this machine learning model, as you can see, we have 3 layers, right? Obviously, before that we have an input layer, and then later we are going to add a output layer, because the machine learning model, the last one, as you can see, is we get basically 64 numbers, and then we have to, based on the 64 numbers, to find out what's the what's the largest value, basically, because this is all probabilistic, right? So you have to, based on the guess for the machine learning network is to say, oh, this one is more like 70% to be a dog, 30% to be a cat, and then based on that information you will say, oh, okay, this sounds like more like a dog than a cat. So I'm going to say it's dog, right? This is just how machine learning does things, right? It doesn't reason like we as human, right? It's reasoning about the probability, right? And then we have to interpret that probability into something that we people can understand. For now, I'm going to build this network. It's pretty fast because you are just defining the network. You're not running it so far. Okay. And then the next one is, I believe this one is to, generate, as I said, you have a neural network, you have multiple layers. For the last layer, even the last layer has 64 by 3, different, that array of information. Later, I'm going to explain what that information exactly means. And then we're going to transform that into a binary data, right? This is just 1 dimension, which means at the end, you only get 0 or 1, right? And then, we use that to get the output, right? So if we go back, look at the whole, neural network machine, this whole neural network model, you have 1 input layer, and then you have 3 training layer, right? This is like, our human brain's neural network. And then you have one last side of it, which basically you can reason, based on your training data, and then you're going to reason and get a decision whether this is cat or dog, right? So this is the rough structure of this machine learning. And let's look at this summary, right? So input layer. So this is one neural network. The second one, the third one, right? At last, we first, need to flatten that out into basically 64 by 3. 64 by 3 should be 64 by 3, right? Convolutional network. I don't know exactly what this means, but we flatten, yeah, after we flatten it, we get this much. And then at last, we try to deduce that number and reduce to a binary decision whether it's 0 or 1 here, right? This part I don't exactly understand so far. We have to basically the point is basically the neural network, right? The dimension may be high, but then you need to slowly reduce dimension. At last, you're going to change the reduce the number to 1 dimension, which is 0 or 1, right? That's the one. And then this is the optimizer that we're using. The optimizer is so for every machine learning training, right? You have to define an optimizer, so that it's a little bit complex, to be honest. I'm not fully understand, and so far, I only know a few optimizers, and then when I do these kind of things, I will just gonna pick one of them, and usually the Adam one I think it's pretty popular, or maybe some kind of cross entropy. That's different one, right? So what does it really do is when you train the model, right? You're going to compare the model. We already labeled the image, whether this is cat or dog, and then when you train it, you found another solution, and you're going to find out the difference between the two. And if the difference is too much, right? The difference between the prediction and the reality is called entropy, right? So it's just about because this difference, I somehow need to define this difference in a number, and then backpropagate, change the neural networks, parameters so that the next round of prediction is more closer to the target, right? This is like if you think about the machine learning training is like a human climbing a mountain, right? And this optimizer and the real training data, the given labels is like the top of the mountain, right? This optimizer is more like a way of guiding the person to the mountain, to the top of the mountain, right? And the optimizer will say, okay, you already reached half the mountain, and the optimizer will look at the top of the mountain and will say, oh, you should go this way, or maybe go that way, right? This is what the optimization does, right? Okay, so we define this optimizer. And the next thing, previously I mentioned that our original data is not exactly 150 by 150 RGB file, but because this training model is limited, right? The machine learning training model nowadays, we can only use the images with the same size. So we somehow will scale it, right? For that, we just use provide the library, and then we just resize it to 150 by 150. And the machine learning training model, we have trained them by batches, right? You cannot just, with 2,000 images, you cannot just feed them into one single model at the same time, right? You probably want to break them into multiple batches, and then, you first train like 20 together, and then do another 20 together, like slowly going through multiple iterations, right? So this is a very simple, like programming kind of a way of doing that. And you may ask, why do you need batching, right? Batching is to speed up things, right? Because the machine learning, the real reasoning underneath it is to train it, underline the curtain. It first go through a forward loop, right? Each one, remember, it's just a matrix. There involves a lot of computation, right? You go from here to here for each data. You train them once, and then based on the optimizer, and you find out the differences, and then you have to backpropagate. You have to backpropagate to the original size. The backpropagate will change the parameters for each model in the middle, right? So the computation is pretty heavy. You could actually, for each image, you go through this one, forward and then backward, right? But to train the whole images, you would have to do that 2,000 times. That's just too costly. So instead, we do 20, 20 images going forward, and then, for that 20 images altogether, you go backwards, right? So this is how the batching works. So just speed things up, right? So okay, so now we define this, pre-process these images and fit into our training. And same thing that we handle the validation data set. Okay, so now somebody mute yourself.
Paul, can you mute yourself?
Thank
There.
you. Yeah. So now we are going through this, real training phases. I'm going to let it run, and I'm going to let you guys ask questions, because this training is going to take a while. So any questions so far? Anyone?
So earlier we were just like importing the images and then like grouping up and setting in the settings for training, right?
This
That what
step,
all
this
this
step,
is?
this step or which step?
Basically everything. The batch size, the images that counts to 2001 or something. Yeah.
So this one is mainly to pre-process the data so that it can feed into the neural network. And before this, I explained the neural network itself, including the optimizer, right? Optimizer technically is considered as it's not exactly the neural network, but more like, a guidance for the, for the neural network, right? How do you train them, basically, right? It's one key component, right? And then we prepare the, the training data, and then we are going to validate this data. Does that make sense, Latia? I'm not sure I explained it clearly. Yeah. So in summary, there are several key components during this whole training process. You have to have your training data. You have to have your neural network model. And that neural network model, it can be described, you just describe the shape. And then you have to have an optimizer that will let you know how do you actually update the parameters for your neural network. And then at the next step, you need to have some kind of validation to validate your trained neural network, how accurate it is, right? These are the several key pieces in the classification problems. So without further ado, let's look at the training. It's done. Okay. So what does this exactly mean, right? So epoch is 15 times. Means that we train that, we train this same, 2000 images for 15 runs. And each runs, obviously you break them into multiple batches. Previously we defined the batch to be 20. So you're going to run basically 100 batches, right? And you run this 100 batches, that's one epoch, okay? And then you repeat this process until you run 15 epochs, okay? So now, can I ask you guys, anybody knows how many batches in total we have run? This should be a pretty simple question. Just make sure that you guys are awake. Anybody want to take a shot? The question is, we have 2000 images, and the batch size is 20, and we run 15 epochs. How many batches we have run against the neural network? Anybody want to give a shot? Okay, so if nobody, then let's do that, right? So 2000 images divided by one batch size is 20. So you're going to run, the 100 times, and then 15 epochs, you multiply 15. So you're going to run 1500, 1500 batches, right? So 1500. I want you to remember that number mainly because this training process is pretty slow, right? Usually nowadays, we use GPU, or in some cases we use TPU to train the data, right? So the training part is the most, the resource consuming part, and it costs a lot of money for training. So just want to give you that kind of concept, right? But obviously today, the code lab that we're using today, we get the free resources, right? Google is pretty generous. So okay, so now since we already trained the neural network, then maybe we should look at what that neural network exactly did, right? Remember previously I explained how we want to find out the animal, and then I look at the animal, look at the characteristics, and then I task we kind of deduce it, right? This is exactly the neural network do, right? The very first step, it will try to identify the, the animal part, right? And then the second part, it becomes a little bit more abstract, right? To look at, the images itself. This maximized part is basically to, this is, between this step and this step, I think there's not too much difference. It should be, because this one is just, so convolutional network is the way that it look at things is it look at the each sector at one time. Think about it when you look at the big picture, 150 by 150. You are not looking at the whole picture, but instead you look at a small rectangle at one time. You shift, keep shifting, right? And for each of them, you somehow get a fixed, you get a number, for that, for that whole area, right? And you can, slowly do this step by step, and recognize. This is how machines, work, right? As you can see, it slowly reduces the size, and then at last, to another round of neural network. So this is to computers, right? This is the information after it goes through 3 layers of neural network. This is how it gets, right? And then based on this one, we are going to basically find the probability, and then predict whether this is cat or dog, right? Based on this information, right? This is how the computers work, right? So as you can see, they work quite differently than us humans, right? So I talk about we already trained the model. We look at roughly how the model works, right? When I say roughly, because you have to this data are, neural network in general is pretty hard to explain, right? We are very fortunate today that we look at these images. We can even display, how the machines look at these images, right? But this may not be always true, right? In some cases, the machine learning model itself just a little bit difficult to display, and it's a little bit difficult to reason about, right? We humans are good at images, right? But think of this is some other decision factor, right? More abstract, right? If you only show the 0, 1 number, right, it will be very difficult for us to understand what's going on, right? So the interpretation so far is still, I believe, is one of the hardest problems in the machine learning area. Okay. So without, let's look at how do we evaluate whether this model is accurate or not, right? So we treat this train rendition and so let's look at this accuracy part, right? So these are 15 epochs. We trained for 15 epochs, and after the 15 epochs, right, this shows how accurate we are in predicting the data, right? And this is a blue one. shows our accuracy in the training data, and this yellow one shows our accuracy in the validation data. Okay, as you can see, when you train 15 times, our accuracy in predicting the training data becomes very accurate. But when we look at the validation data, after some apple, right, that number pretty much, be stable there, right? It doesn't change much anymore, right? So this actually brings up another kind of difficulty in the machine learning training world, right? So with 2,000 images, right, it's actually a small data set, if you think about, in the machine learning world. Generally, in the typical nowadays machine learning world, we train data using at least millions of levels, right? That's called, deep learning, and we have to use that amount of data. But in this case, we build a small model with 2,000 training data. Even if we train the machine learning model to be very accurate on the training data, but then we look at the validation data, when we apply it to the real life, right, its accuracy is only around maybe 70, 74, 75, right? That's the limitation, right? Now you understand, okay, small amount of data, no problem, you can still train out something, but the model that you trained may not be that accurate, right? I bet if we can feed this, feed this model with more data, let's say maybe 1 million, right? I believe we can significantly boost our accuracy for the validation data, right? So that's the rough understanding. I won't explain the loss part. Accuracy is pretty easy to understand. Loss is a little bit difficult. I will defer that. For whoever, if you're interested, you can look at what does lose mean, right? Think of dimension. You have you predict to be true, you predict to be dog, you predict to be cat, but in reality it's dog, in reality it's cat, right? And then depending on how you summarize the data, you define the accuracy or the loss, right? So for accuracy, obviously the higher the better, and for loss, the lower the better, right? So okay, yeah, we talk about overfitting. Okay, the last one is to kill it. But for now, I'm not going to kill the machine for now. Even if you don't do it, at the end of the day, the machine is going to be recycled after long time no activity, right? So far, we have gone through the whole process. I want to re-emphasize what we have did. We talk about the training data, we look at them, we talk about the machine learning model, and how we define 3 different layers. And then we talk about, how we use the optimizer to help, change the parameters. We talk about how do we normalize the data so that, all of the, images of different size, we turn them into 150 by 150 to fit into the neural network. And we talk about, how we train them, how many times you should train, right? In our cases, we use 15 apples, right? But maybe some cases you want more, some cases you want less, right? And we talk about how we can batch the things to speed things up, right? And we also talk about, how we can validate the trained model, how accurate they are, right? How useful they are, I should say, because accuracy and loss are 2 different terms. So using accuracy can be confusing, right? So how useful this model is, right? And if you have too few data, and most likely you're going to face this overfitting problem. Overfitting means that you get pretty good accuracy for your training data, but not so good for your validation data, right? Okay, so we have done this, code lab, and I would like to pause here for you guys to ask any questions or anything you want to, not specific to this code lab, or anything else you want to discuss. Any questions?
Is the only way to prevent overfitting just dump a lot of data on it?
There are two ways. One is you put more data, right? More variety of data. And another way is you don't necessarily need to define a quite complex neural network, right? So there are two ways of solving this problem. In some cases, the neural network is defined to be too complex, which if you think about this, right, it also works, right? If you have enough data, right? Eventually you can still get the result. It's just in that case, you would need way more data than a small network needs. But said that, the flip side of a simple neural network, too simple, is even if you feed more data, you cannot get the correct result, right? So finding out the right neural network, it turned out to be more like art nowadays. Tons of data scientists, machine learning engineers, right? They explore the different parameters, and even nowadays there's actually a new technology called AutoML. Their job is to automatically find out the best parameter, the best neural network structure, right? Yeah, but that's another topic we can discuss more. But very good question, Matthew. Any other questions? Okay, I'm going to stop sharing. And pause here. Anybody else want to talk about, after you learn this code lab, what we could use similar machine learning techniques to do some other things, fancy things? Any idea?
Well, I know they use this stuff to build like chess engines.
Yes. Kevin, that's very good one. Chess engine one is actually that's called reinforcement learning. I'm not so sure actually we can actually do that, because that requires much more complexity. Previously, I tried to train a model to play, Chinese chess. It turned out that it's not that easy. We could talk about it, in the future, maybe, right? Or maybe you guys can go back and read the website. There are some explanation of them. It's pretty fancy. And I can say that even if using machine learning to train deep neural network, to play chess, I cannot beat that. So I can write the program, maybe train the data, maybe get a kind of neural network to play the chess, but I cannot play that as good as them.
Maybe something that applies more to our FTC, maybe be able to detect what game element the camera is looking at, maybe. So for autonomous, it can be better.
Yeah, that's a very good idea, Eric. We could, yes, we could actually, for example, this year, right? We talk about, is it possible to look at, the cube as, which one is heavier and which one is lighter, right? I guess you guys already, think about that a lot, right? But maybe one of the ways is to, look at the images, right? To see, whether this one, has iron there, or how many irons there, right? You could predict that. Right? But that's very good one. Anything else you guys want to? You think of? You guys are interested in? What do you guys think about this code lab? Is it useful?
I think I like it. It's pretty hands-on. Like you can really work through it without like programming the lines yourself.
Right. I'm glad to hear that, Kevin. Yeah. Anybody else want to point out maybe what is are there any areas that we can improve? Okay. I assume there's no more questions. So yeah, if there's no more questions, that's all for today. I really appreciate your time in attending this, this small talk. And
Yeah, thanks, sir. Thanks for doing this for us.
of course. Bye, guys.
Okay, bye. Have a nice day.
Bye.
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 Thank you.
Thank you.